The last time I tried to create a purple compound, it went horribly wrong and everything turned into a depressing gooey mess. But this time I have something new in mind. This is the cousin of the permanganate ion, called ferrate 6. As the name suggests, it contains iron in the +6 oxidation state, which is rare and strongly oxidizing. In fact, it is stronger than ozone in an acidic medium, with the capability of oxidizing water to oxygen at room temperature. Currently, its potassium salts find use in the water treatment process because of its ability to wipe out pathogens without leaving toxic byproducts. In this video, I will try to synthesize the sodium salt of ferrate in solution through electrolysis and attempt a simple characterization. So here are everything I'm going to use in this experiment. Electrodes made of iron, a 9-volt battery, wires to connect these two, enough sodium hydroxide or potassium hydroxide and water to create an approximately 25 molar solution, which is really dangerous, so be very careful. And last but not least, a container. Here I'm using a thick polyethylene one, which is pretty much inert against concentrated solutions of hydroxide, at least much more so than glass. The moment I complete the circuit, a brown crud of iron oxide floats away from the anode. This is followed by the formation of the reddish-purple ferrate ion, making it look as if I'm turning water into wine. Due to the placement of the cathode, this won't be the most efficient cell, as some of the ferrates got reduced right back to the lower oxidation states. As you may have noticed, the cathode is bubbling a lot, but not the anode. You can see this more clearly in a side-by-side comparison of the two. In another run where I used a much less concentrated solution of sodium hydroxide, the anode produced a whole lot of bubbles as well, which is a sign of unwanted side reaction, showing that energy is wasted in the oxidation of water or hydroxide instead of iron. Not only that, the oxygen involved passivates the iron anode, slowing down the reaction and lowering the final yield. This is the reason why such a high concentration of sodium hydroxide is required if you want to get a decent amount of ferrate in the end. However, I'm not really sure as to why this happens, but my guess is that at lower pH levels, the oxidation of iron to ferrate takes more energy than the oxidation of hydroxide to oxygen, which becomes the favored reaction. If you guys have any thoughts, I would love to hear them. After 6 minutes, I stopped the electrolysis because the battery was getting uncomfortably hot. As you can see now, the solution has turned a deep, almost opaque purple, similar to a concentrated permanganate solution, but a bit darker in color. On a side note, sodium ferrate is way too soluble in water to be isolated as a pure product without significant decomposition, though it can be precipitated with a soluble barium source like barium chloride or barium acetate, but unfortunately they are pretty toxic and I don't have access to them. Here's how the solution looks under a flashlight, which makes it appear more purple than black, though for some reasons the opaqueness didn't go away. Now I'll try a reaction with sucrose or table sugar. The same reaction with alkaline potassium permanganate is known as the chemical chameleon, where you can see the purple color first turning green, blue, and then brown as the oxidation state decreases step by step from manganese 7 to manganese 4. But for ferrate, the purple color simply faded, turning the mixture mostly clear with a light yellowish green tinge, which could be ferric hydroxide or some other high-valent species of iron below 6+. Despite the fact that sucrose is a non-reducing sugar, this is not really impressive because the basic medium hydrolyzed it to glucose and fructose, which are very easily oxidized even by copper 2 ions. But still, this test confirms that the purple stuff is indeed an oxidizer. Next, I diluted another part of the solution with a large amount of water. Even though the pH was still basic, this purple color was fading by the minutes. Again, this would not happen with potassium permanganate, which is much more stable than ferrate in acidic conditions. Before it fully decomposed, I added some ammonium dihydrogen phosphate into the solution, which should increase its oxidation potential by acidifying the solution. Due to the low concentration of ferrate, reactions were hard to see for the first few minutes, but eventually the color faded and a lot of small gas bubbles evolved. The lack of ammonia smell suggests that ferrate oxidized both water and ammonia to oxygen and nitrogen, respectively, which I think is pretty cool. In conclusion, everything in this experiment went pretty smoothly, considering that this was only my second attempt in making this compound. This will be the first video of me talking into the mic, so tell me what you think in the comment, and apparently this will also be the first English YouTube video on the electrosynthesis of ferrate 6 in more than a decade. So enjoy, and I'll see you next time.